Hi, this is Nileparik. It's been long since I have recorded my last YouTube video. Today, I'm going to discuss one of the key components which I have discussed in length within the article called 2024 Data Engineering Exploring the Key Impact Radar. So if you haven't looked into it, please feel free to visit on my website. It's available there. And this key impact radar has one interesting element called data observability. Beyond the data observability, it also demonstrates that there is a cross section between the edge computing, decentralized data, machine learning, and data observability. And this is the point where we talked about that age-driven real-time AI ML applications. Now, what do we call age-driven? Age mean to say where the actual computing is taking place or where the action is taking place. And of course, the artificial intelligence machine learning means we are putting some mathematical calculations or statistical or some sort of a regression around there for identifying patterns or optimizing solutions. And of course, the data observability belongs to what we would like to observe. So that just doesn't mean the business data, but also the ML data. And there is a talk of town, MLOps. I think a lot of time I speak with various industry leaders, thought leaders. I think everyone talking about MLOps. And for right reasons. I think MLOps is going to be one of the key area in next 2 to 5 years. And I think many companies are seriously taking MLOps into their portfolio as well. So without wasting time on that, today I brought interesting implementation. So this particular implementation was a part of my broader research going for one of the leading quantitative analytics and investment firm. Um, and I'm been tasked or actually been asked in both ways that how can we build a real-time observability system that can provide consistent data pipeline output as well as most optimal infrastructure solution on cost too. So I thought might be the best idea that because we were piloting Quant's platform for that company, and I said, why not we just start recording a couple of quantitative analytics algorithms, try to establish some good application telemetry, and let's deep dive into the solution. So what we did is basically we plugged in, and if you can recall the previous videos where I have demonstrated this architecture as a Quantex, where there is a big observability component and that picks up open telemetry component which constantly push the data out there. So using this component in our pilot, I instructed the team who is responsible for implementing that to capture the data, and they actually successfully captured the data for me to take my research forward. And that been captured with a couple of algorithms which the company was implementing. Alpha research, which is basically a profitability algorithms, market data evaluation, which is L2, portfolio manager is a modern portfolio theory, various quantitative analytics, risk assessment, more risk modeling as well, and a couple of statistical modeling as well. So they basically bought this all a data, and that data include what model it is running, which system it is running. So that's going to be static. Then it says that what is the runtime in second, run IDs, run timestamp. Most importantly, that the figure that we are looking for is CPU consumption, memory consumption, how many threads been used. So this is an interesting parameter, and I'll come later in the video why I requested them to actually pick up the thread, and then parallel ID, because quant algorithms generally run in parallel. though the risk assess doesn't run, risk modeling does run. It runs up to 50 parallel 50 parallel containers for one schedule, and every container can run up to 8 to 10 threads as well. So it's like almost 400 to 500 threads that build the risk model. It is one of the quite powerful quantitative algorithm that we are supporting right now. But I think another one is the market data evaluation, because that's also the L2 level algorithm, and that handles the fluctuation and the different frequency quite often, because if the market is liquid, it gets a lot of depth, high depth of L2. If market is not liquid, it doesn't get like the depth that generally we anticipate there. So these are a couple of algorithms which I thought might be useful to realize and analyze. Now, with this telemetry data, it's not very difficult for anyone to find out this kind of telemetry data, that what is a CPU consumption. So it says 466, means with some sort of a standardization, we built this particular design architecture where we managed a couple of dry runs. We captured the historical computer telemetry and business telemetry, trained the model for the back testing, put up the model for machine learning in ops, which can forecast 15-minute resource projection. And then that resource projection can be pushed to Kubernetes controller, which is Kubernetes is one of the core component for the model execution, and which is deployed as the controller itself, which manage the number of the nodes and how the load should be distributed. So we are not using the standard Kubernetes distributor, but we have developed our own machine learning based distributor for higher edge results. And I'll come back on this video that why we actually took that decision and what are the benefits. However, it can work with the Kada or any other Kubernetes distributor quite successfully as well. And this is the telemetry that you're looking is the only compute based telemetry. There is a business telemetry which also we include, for example, like how many depth or what sort of an open book we got, so like order book we got, and based on a number of the order book we also adjust the compute requirement, because we know that certain level like there is a correlation between the orders and the compute take place, and also we make some of the dry runs to constantly validate our data as well. So this is the architecture which basically bring back the conversation where we started, is the data observability machine learning, where we actually build those component, and the edge computing, so that push all three components. So this is the edge computing, where the live optimizers stick with the Kubernetes and influence. This is the artificial intelligence modeling, where the machine learning weights been trained based on a dry runs, computer telemetry, and business telemetry. And this is where it's been deployed constantly at the data ops, where we are getting the live data observability using compute and business telemetry and the live and it basically pushing via the machine learning in ops model, which is the 15-minute resource projection, that what kind of a resource we could anticipate to come in next 15 minutes. So that's the whole setup that we got in place. And now I'm going to show that what we did and how we actually help a client to actually significantly reduce their cost. Let's deep dive into that. So this is what the raw data of each and every service. It's like a 5 days worth of data, and I think you can see that we got a quite number of like 4,000 5,000 row per algorithms. So let's start with it. So first of all, we'd like to explore the data, what data looks like. Sorry, we are going a little bit of into data science, but I think it's worth it, to be honest, to understand what we did and how we actually achieved the whole process. Having said that, this is what I'm showing you is a mini version or actually a micro version. The actual solution that we have delivered is far complicated, and actually it covers many other edge cases that I'm not going to discuss in this for just maintaining under 10 minutes. Um, so, well, it reads the data, that is the market data evaluation. This is how the data looks like. The job ID, controller that it is. We discussed about the controller. So yeah, it's a ESX in-house controller, ergo some X labs controller. It tells like what was the runtime for each job, run ID, run timestamp, CPU consumption. So it basically consumed 4.46 vCPU equivalent of ticks. Memory consumption, how many threads it run, and what was the parallel ID of that job. So parallel ID is basically the number of the Dask container that has been spun off, or in this case it's a Spark, so number of the Spark containers it parallelly spun off. Uh, um, just doing some sort of a data cleansing, and then we are putting the historical plotting. Now, interesting, the runtime distribution, what it tells. Now, take your time. This is a very interesting conversation, I would say. If you are interested into MLOps, if you are interested into AI ops, if you are interested into how to make your system better in operations, I think this might definitely will spark some interest into you. So now let's go back to data. What does this data distribution tells? So this is the distribution of the runtime. So runtime in seconds. So at the beginning of the video, I said that one of the key requirement was that algorithmic traders and system traders has set on every algorithm an SLA. We do not like to continue, we do not like this algorithm to go beyond 120-second runtime, 150-second runtime, 30-second runtime, 50-second runtime. But then any job, that how long it run depends on how much data we ask to produce, or data we throw at it. Well, that was the real challenge, is it doesn't matter how you can build a framework and how you can build the infrastructure that always ensure my quantitative jobs are running within that plus or minus 10% SLA up to 98.5 percentile. Because on those numbers, I can backtest against the actual market data, and I can see that my solution is very profitable. Because if this NFRs doesn't meet, or if even 5% degradation happened to these NFRs, the whole profitable scenario that we derive from backtesting will go into negative zone. And I think this is quite naive mistake. We see people who are not very familiarized with the algorithmic trading or system trading. They do backtest, and in a backtest, it's like a laboratory settings. You always get a best result out of it, right? And looks like, oh yeah, system looks very profitable, but there is a latency that we haven't seen. We haven't competed in the actual market against other people's performance. Plus, what about IT system going down? And there is a blackout, there is a data blackout, data blinks, data freshness, refreshness, whatever it is. They all matters into ultimate profit number when it comes to system trading or algorithmic trading, or system trading specifically heavily dependent, if it is heavily dependent on the algorithms and the insight and the market intelligence that been generated by your solutions. So to solve this was a clear ask for a research, that how we can achieve it, and can you prove in your research that you have achieved it. So that's the very first evidence that we generated, was this runtime distribution. And that tells that we have successfully achieved the distribution towards the left aligned pane. That means the left side is the lower end of a runtime, and you can see that majority of the 98% of distribution is happening between that. So it is actually happening between 1280 to roughly around 1390, and between that the majority of the distribution happens. So this is how actually you can put your MLOps systems or your live dashboard system, where you can actually validate whether the system is following under the correct distribution path. Now, if my system is unstable, I would not see this kind of a left align distribution. I would probably see somewhat right line distribution, or um, there is a possibility the middle distribution is also possible, because there could be a one or two edge cases on the left side and then start. But what we actually want is optimization to be starting from the left, the far left corner, not from beginning. So I think there is a small bar here which is not visible, by the way, but there is a small bar here as well where my cursor is. But it is immediately starting the largest spike. So you want to see this largest tower in a first three of them, and then subsequent tower coming, and then that's it. So the shorter the distribution is, the better your system is. That tells your application is good. Now, the scattered plotting. Now, this is quite interesting area which I really like always. CPU consumption versus thread and box plotting. Now, what it tells, like, if I have to go into every application and read line of code and say, hey, you know what? Is your code better? Is your code good? Probably gonna take ages, and it's gonna probably, I'm not sure whether it's gonna plummet their banks. I think they're quite deep pocket guys, but yeah, it's like consultant like me or many smarter people than me who might actually cost them even more fortune. uh, possibly possibly are not worth to go through every line of code. So in that particular component, I have developed certain intricacies where it can pick up patterns, how the CPU and memory consumption picked up, and based on that I always draw these box diagrams. This box diagram, the better the center the distribution that comes into box diagram, it tells that CPU consumption versus thread is in optimal. So it tells me immediately that whoever is writing a parallel programming is writing in a good way. So it tells me, like, if it is a 8 thread, then it is not probably the best. It is optimally processing, because all you want to see is the left top distribution and the bottom distribution far. You want to actually see the box smaller and the middle mean line in the middle of it. So ideally, out of that, the sixth thread is the ideal out of 4. But this is good. This is not bad, in my opinion. This is still good. Then memory consumption versus thread. So how it goes, and you can see the memory consumption is perfect, absolutely perfect, because there's not much thing has been done. So it is actually a work of C++ developers or the actual core library components. So it is coming like almost perfect. So this is your god bar. So like you really want to see every bar like that. Uh, and this tells me that how good the code and program on threading is. So I don't need to look into it much. Then I always write this heat map, and actually, because I have turned down the data a lot, so I'm just showing you 3 graphs. But I think when I will be publishing, just let me break the news that I'm going to publish another book by end of January or the first week of February about MLOps. And this is going to take, it's a CXO series book again, so it's like 150 to 160 pages with 8 to 10 chapters, and going to cover this sort of a concept very much in detail for CXOs. Like, okay, what you should ask for your dev teams to build, to see like what is the health of your application, especially if you are in the competitive business, such as like algorithmic trading, market finance, fraud risk detection, payment systems, or anywhere else. Or if you really like to build a good system, why not? Means you don't have to be in these fields. You can be any fields, and equally you can build smarter systems. So this is where it comes in, and what we are looking for here is called the problem that I described. That okay, what about if my data influx is double, and I'm still being asked to process between, okay, your system should always process at 1300 seconds. It should not take more than that. But what about if I get double of the data, etc.? So the Quantex, this is actually a capability of Quantex, and I'll explore that later, which automatically distribute the load accordingly. So the algorithms, if algorithms are compatible, then it can distribute the load automatically, and it can multi-thread the process automatically. And this tells us that when the load increase, it automatically expanded the number of the threads. So vCPU's engagement increased, but it was successful to maintain the heat map in this oval shape successfully between the SLAs. And there are a couple of like a out of the box cases as well, where you got a 2 dots up there, but all you're looking for is this hot dog shape. If you get this shape in general, and I'll show you some of the other shapes as well, which are quite interesting, and I'll also explain you why that is happening, especially in the context of algorithmic trading. So as long as this shape appears, your system is in good shape. Your system is performance system. So let me show you a couple of others, and I will go through each and every one. Is this one, and it's explained like market data eval. Now what happened is market liquidity depends, a market based on market liquidity, the L2 data's depth is vary across the whole day. So this tells me that how I can see that my system behaves and how well it behaves because of this individual clustering patterns that is building. So you can see that the 6th thread, the individual cluster patterns, at the 7th thread, it's the strongest pattern. 8th thread, it's a light pattern, but there is still a pattern, and 9th thread, it's a pattern. So what it tells that when the market liquidity increase, I can engage 9 vCPUs to process my market value, market depth data, and that goes as smooth as possible. So if this is like a triangular shape, or if it is not in this like a don't get it wrong, but this is a sort of a, I'm gonna call it I'm gonna keep it named as a hot dog shape. So as long as it is in hot dog shape, or if it is not in hot dog shape, yes, your architecture, your system, your application need to be looked into. Definitely you should review that, why it is happening, because this is what it tells, is distribution is very clear, and that means it's reassuring, and it tells like the majority of the time market depth remains here, and the seventh thread can manage that market depth very easily, and the second best possible is the 9th thread, and then you can see that sometime it goes even below, and sometime it's tend between 8. Alpha research, as I said, like profitability validity, and this is quite interesting. Why this hot dog appears like that? So there is nothing on 4.5. It's like me being lazy, not removing the integers, not keeping on the integers. So what it tells, the vertical and horizontal. So any services, if you're building a heat map on any services, that what is the performance on the live ops system. In this system, if my order book has a lot of open orders, or unclosed deltas that I need to chase up, that will perform a vertical, because that means my order book is quite depth, and that means I need to process more data. And the y-axis spread also explain if the market volatility is high and I need to go via certain additional multimodal algorithms to get that information, then I will end up here. So you can see that there is a pattern appearing with market data and order book. So order book and market data is describing the vertical and horizontal spread of this kind of a uh, implementation. But yeah, portfolio manager is basically a modern portfolio theory, similar thing, and portfolio is pretty much static, like not no portfolios doesn't change that often. I mean, short term trades does take place, but portfolio doesn't change that often. So portfolio shows me that there is a strong consolidation of heat at one place. That tells me, yeah, it's good. It's good code. It's a stable system. It's been stable infrastructure, and it's supporting and it's doing exactly what it's supposed to do. The same as what we discussed on that alpha process. This also goes by order depth, so like open orders and the market depths. And I think this is a perfect distribution of risk assessment, because risk assessment happens on throughout the day, and yeah, it's a sort of a it's a good distribution. And the same that we discussed. Uh, so yeah, I think this heat maps, especially around the live telemetry, tells you a lot of information. So again, if you go back on our original diagram that we were discussing, why age-driven real-time AI ML applications are key. This is exactly the reason. I have shown the example of operational uh, application in ops, but this is also the same applied for the algorithmic trading and other thing. And if you see the importance of that second level age driven, this is exactly what it is explaining. The data can be analyzed and acted upon in real time, revolutionize the industries like automation, automotive, autonomous vehicle, industrial automation, and healthcare. The real-time data observability, and this is where I was quite emphasized on that, ensure the data quality and performance optimization. It is very easy to detect anomalies and bottlenecks as they happen, and this is exactly what we are trying to achieve. Because when a system is responsible for $100 million worth of trades, a green, red, and amber lights are not sufficient. We need a representation of visualization that can be interpreted, not validated. So, status is subject to validation. True visualization is subject to interpretation. It should tell us exactly what business is doing. That's why my systems are acting in this way. Or if my business is doing this, then my system should act in this way. This two-way verification should be there. And if it is not there for any critical system, then there is a gap. There is a gap. There is a possibility of a blind spot. And that's why in modern age, and I think we will see this more and more MLOps. We will see more and more AI ops coming in, and this is a true example of it, what we would like to achieve. Now going back on the original point that we are trying to say is like, okay, all thing is done. You shown us excellent example of a live optimizer and how you are validating everything. Oh, that sounds good, but how we can establish, how we can use this information to even go further and beyond a stable system that we can validate, how this system can be proactive and ensure that there are sufficient vCPUs are available, on the clusters that we are building as we anticipate the more processing requirements are coming in. Well, for that, I think we're going to look into this particular piece. So what this does is I have minified the whole area. As I said, like I have only taken 10% of the features out of the telemetry that I'm generating, because it was like sort of a proprietary. But this should give you a rough idea that how anyone can build this kind of a pattern very easily. So I'm stationarizing it, and so basically this is a time series coming through. I'm applying the stationary application on it, and then resampling at a certain point. It's a 1 minute resampling happening, and it transforming that number of the CPU consumption that happen as an average CPU consumption across between this runtime. It will spread, and it will generate a kind of this is a small one. I'll show you a kind of a time series. So it is transforming the application telemetry into time series, which tells exactly at any point of time what is my expected, or what is application consumption is. So 19,431 is approximately, it's telling me at 8 o'clock I'm consuming 19 vCPUs, 194 vCPUs as of today, or as of that point at this 1 minute, and I'm consuming 31 GB of RAM for processing that, and I'm running 475 threads within my application to support the current function. Now this is where I said, like, I've already extracted three features, but actually when the model I built, that has more than 37 features, combining many other parameters, business parameters, and all sort of stuff as well. And I'll explain you why it is important as well beyond this point. But this optimization will show a significant improvement where it can be. So as you can see that it goes, and then I have just plotted it on this one, and what it looks like. Let me just quickly reshape. So I have got second, third, and the fourth Jan data, only 3 days data. And as you can see, if I basically go and explore, sorry, this is Plotly. So let me explore this. You can see that how does it look like, and there is certain patterns that you can see. Based on this pattern, the machine learning learn pretty quickly. So let's explore. I think let's avoid memory at this moment. Let's just focus on the CPU and other. So this CPU patterns, it tells exactly like what every minute my CPU consumption looks like. And as we already saw that, yes, all the memory, while the CPU consumption is going, our application is very sufficient and capable enough to handle that. As long as the CPUs are available, our code is good enough to do multi-thread, multi-process, and produce the results within the required time frame. And it also tells like how many threads are running and what is the optimal value. So there are a couple of other optimizer in terms of like mathematics I have built as algorithms, which can take those inputs of CPUs and number of the threads required and other elements around that, locks and all sort of stuff, and thread wait times and sort of thing, idle time and sort of thing, and it generates an appropriate profile based on the application performance itself, and that brings out of the dry runs. So if that dry runs run, so dry run happens at every time we build the model and the production pipeline, it basically refresh those parameters and also stuff. But without going into much detail into there, this is what it does. So you saw that what is happening. Now based on that, I have written this very basic. So actual optimization pattern is way complicated than this, but I'll walk you through what the idea is. It actually explained the idea. So I have put the Microsoft Azure SKUs that we are using. So what SKU options are available? D, E, F series, all sort of stuff. And because I'm only providing a feature as a RAM and CPU consumption. So as I said, like there are a lot more features that we have actually built, and some of the composite features as well, and constraint as well. So that the real optimization got a lot more complex data to process inside it. But for demonstration, I think this is very easy and explain what it does. And it calculates the maximum vCPU and memory requirement for a 15-minute window. As I said, like this actually project 15 minutes, and this calculate 15 minutes. Then we are doing the optimization problem. Is like how many VMs and how many VMs I should select. And this is where I think you're gonna see the real value where I'm coming from. And this number is actually multifold. Where is the optimization? I'm using Pulp as LP optimizer, and as you can see that, yeah, it's perfect. Let's optimizing it. Not going into the algorithm much. You can take a screenshot and probably read it. And I'm gonna publish this code as well with my book blog as well. So you have to just wait for a couple of days and then it will be. But let me run it. So I'm now running it. Yeah, that's it, done. It's run. So the whole optimization actually run, and you can see that the final value, what it told us based on this data, it tells us that put 12 of standard F16S V2. So now it's smartly selected between the general purpose, memory optimize, and CPU optimize. Use CPU optimize. Why? Because your usage pattern appears to be better optimized with the F series, and I think we will smartly also test like what it does. And it also identifies that there is a a liquid provisioning can be done, and that liquid provisioning can provide you some sort of a cost benefit. So it is suggesting that on an average, put your 5 liquid provisioning on F2 with 2 CPUs, so it can smartly switch up, switch down. And this logic of optimization with I think said many additional parameters does exist here, optimizer, and that controls the physical VMs that probably going to cost you. So all I have done is also I have put a cost in front of them as well, which are actual cost in dollars as of today in Azure, and it calculate me and give me a cost that if I have to run that, it is going to going to cost me. Let me increase the font size, so I think anyone looking into it can see that. Right, good. So yeah, the cost. Okay, let me put this back and let's see this. So it show the cost of 5898, so 5,898.40 dollars it will take to run this too. Now it's interesting because it's actually giving me the most optimal cost at this stage. In constraint, the actual algorithm, there are many constraints. So it was third or fourth because I want to make sure that there are a couple of constraint applies to as well. You can apply those constraints and you can build your combination accordingly. But now what if I basically tell this algorithm and say, you know what, F2S is no good for you. I don't want you to use this. And I'm just going to put it down and I'm going to run it. Okay, let's see what it tells. So then it fell back on D2DV4 because instead of falling back on F4S, so it fall back on 2F4S because 2F4S were cost effective, of course, but it has reduced its flexibility with only one D2D and said, okay, this is going to cost you 5916, this combination with this kind of implementation. But the earlier one that we saw was at 5.8 something, which I'm just trying to get there where it is. 5898. So now we got a difference of around 20-25 pounds, dollars. It's not something we could have fight, because the infrastructure that actually I optimized was having around 18 million annual cost of compute only for running the quantitative and algo trading. So yeah, that you can see the magnitude of the number, how much it could make a difference. Now um now interestingly, if I say, okay, you don't have a choice, and this is where actually things happen, and people think, oh yeah, it's still optimized because we are using all optimized methods. But just let's see how important to understand your relation between CPU, memory, locking, waiting, idle scenarios, and other things. So I'm just commenting F2, and let's run it and understand. So we are on the 5.9 something, and suddenly the moment we move on D16 and D2, which was F16 and F2 combination, now if we switch to D16 and D2, we immediately move to 7741.65. So that is roughly 2,000 pounds, a $2,000 increase. Now let's say um, if you got a 20 million annual virtual machine compute budget as a whole company like this, this is an increase of 40% from 458 something to 77, which is roughly around 35 to 40, between 35 to 40%, precise around 37%. That is a lot of money. Lots of money, just by picking up the right combination. And if I may say that, I think this is how sometimes I discuss with people, and this is how they do as well. So if I go and say, you know what, just take this out, you can't use it, just use D8s. And if I run D8s, now just see that if we do not standardize this approach, how much. By the way, now this is quite interesting. So I blocked that, and it find another combination. I did not anticipate it that, but it brought it. It find another anticipation that based on your workload on various, I can also distribute to this kind of a combination, which is one E2D V5, one 12D16, and one V4. So if you use this combo, I can make it 7756. Now I have to probably block that E series as well, which is appearing to be a memory optimized series. So let's say okay, let's block that E series as well. Oops, E series as well, and now run it. And now if you run it, it just say 13 this font, so 7971 and sort of thing. Now let us say that I also say, okay, D16 is our standard and we do not want anything other than that. And I think many companies does this, and if we do something like that, we can see the fluctuation within the cost that happens is like D16 30. Oh, sorry, D16 was already in use, right? So you can actually see the kind of impact, that how many D34, 35. So it increased by 1,000. So what it does, it actually increase the room for idle. So what this particular algorithm does with certain parameters, it is trying to identify that this is my operating system cost and everything via the dry runs and optimize your infrastructure to be used within the 5% of the reserved buffer. So in this way, your infrastructure has never need to be revisited by a human to be optimized. To be observed, yes, we are not replacing human. To be observed, yes. To be intervened, maybe in a rare cases. But to be optimized and assessed every time, no. This system can actually go very deep and can pick up many uh, uh, many interesting nuances, such as like your system might be very consumption memory sensitive and it needs a lot of memory, and also this can automatically switch to E series because it finds that yeah, vCPU and memory ratio is better here, let me optimize. So this optimizer is all about getting this right, and this is a very basic optimizer. And to be honest, even this basic optimizer can do better job than human by spending hours and hours to find like, okay, what is my infrastructure's best optimal solution, and this is it. And what do we do with the context deployment with the Kubernetes and the Spark is we actually build this machine learning based optimization, infrastructure optimization itself in a solution. And this is what I was researching for last couple of months to ensure that yeah, how it can be done. And we in-house develop certain algorithms to come up with that kind of ideas. um, so yeah, it's a quite interesting project for me. I learn a lot actually from here. I'm a data scientist but not a data scientist, and uh, I have no direct engagement with ergosum, as I'm a I have an interest as a investor, but I'm not employed or directly engaged with ergosum. But I learn I lead the research independently for many, as an independent consultant and the researcher. But just as a disclaimer, otherwise, yeah, it's wonderful, and I'm going to publish this deep article into Dataverse, which is the newsletter. If you haven't subscribed it, please do subscribe. It will be fun to read this, and also look forward to the machine learning MLOps book, which is also describing this kind of a very interesting machine learning applications. Small application with a quite large impact area for your organization. So please wait for it. I think it's going to come most likely towards the end of January. And yeah, I'll see you on my next vlog. Till then, thank you. Enjoy your time and keep learning.